Yo, what's good? Welcome back to another episode of How to Algebra. Today we're diving into the captivating realm of geometric sequences. Picture a chain reaction where each term is multiplied by a common ratio to get to the next one. We'll uncover the secrets behind finding the ratio and also calculating any term in the sequence. So gear up, sharpen those pencils, and let's unravel the mysteries of geometric sequences together. Let's get it. All right, so let's talk geometric sequences. So let's just recall what a sequence is, right? A sequence is just a list of numbers. And it typically looks like this. The first term, a sub 1. Second term, third term, ... all the way up to some a sub n. All right. Let's just note that the term prior to a sub n, we can call a sub n minus 1, where the a sub whatever, this is just the term, and then the lower little subscript, the n, this is just the index. Right, it's no mathematical value, right? It doesn't hold any mathematical operation or anything like that. It's just a placeholder. Like it's a number in line. It's a number in line, right? N equals 1 is the first term. N equals 2, second term. N equals 3, third. All the way up to the n term, like the nth term. And then just know that this a sub n minus 1 is the term prior, the term right before a sub n. You might even see sometimes a sub n plus 1, right? The next term in line. All right. So geometric sequences has to do with what happens in between terms, right? Like what gets you from one term to the next. If you've been keeping up with the series, and then you'll notice that or know that in the prior video, we did arithmetic sequences where you have a common difference. You have to add a value, a constant value from one term to get to the next. Well, the same idea applies for geometric sequences. Instead of adding or subtracting a number, we have what's called a common ratio. So a common ratio is going to be some term, right, in the sequence. And when you divide it by the prior term, the term right before it, this will equal r. That's the variable that we use to denote common ratios. Okay, so if we have an example, here we have a sequence, and actually, this is all right, this is better. That was an arithmetic series. All right, so here's a geometric, or sequence rather. Here's a geometric sequence. We notice that it's a list of numbers. And if we follow this pattern, if we can see a pattern, what would the next term be? So right away, we notice that to get from one term to the next, we multiply by 2, right? Times 2. 10 times 2 would be 20. 20 times 2 would be 40. Times 2 would be 80. 80 times 2 will give us 160. So 160 would be the next term. All right, so this is a geometric sequence. Mainly because, so this one was kind of obvious, right? We can look at it and usually see, okay, it's times 2, right? It's times 2. But what if it wasn't obvious? Well, then you take any term. So I'll just grab a term, right? So let's just say 40 divided by the term before it. And we see, oh, it's equal to 2. So now, everywhere you check, right, the first term and the second, second and the third, third and the fourth, and so on, the ratio has to be 2 everywhere. So here, R is equal to 2. But that would be the ratio. That's pretty much it, right? The two things that you're going to see that you may be asked to create is an explicit formula for A sub n and a recursive formula. All right, so first off, an explicit formula for A sub n is going to look like this. So any term in the geometric sequence can be written as the first term times the ratio raised to the n minus 1 power. So this is an explicit formula. So any term, right, A sub n. So for instance, if you did, I don't know, like, let's just see, 1, 2, 3, 4, 5. So if we want to do the sixth term, the 160 that we found, if we want to do the sixth term, well then A sub 6, right, because that would be the sixth term. A sub 6 is equal to the first term, A sub 1, which would be 5, times the ratio, which would be 2, to the n, which is 6, minus 1 power. So 5 times 2 to the 5th, so whatever 2 to the 5th is. So what is that? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5 times 32, which would be 10, carry the 1, 15, 16. So 160. And that's exactly what it is, 160. All right. So you can find any term using this formula. The recursive formula, it's a little bit more intuitive, I think. So if you think about how he first found, like from looking at the sequence, saying that, okay, 160 is the next one, right? Because you can kind of quickly say, okay, it was times 2 to get from one term to the next, and 80 times 2. So 80 times 2 would be 160. So that's basically what needs to happen, right? Any term, right, A sub n, you pick a term, it doesn't matter which one. Well, if you take the term before it, right, because that's what we did, right? When we were looking for the blank, the 160, we had to look at the term before it, the 80, and then multiply that by what? By whatever the ratio is, right? So times R. And this is the recursive formula, right? Any term can be written as the term before it times the ratio. So I guess you want to see an example of this one. This would be, so for instance, so A sub 6, the sixth term is going to be equal to the term before it. So A sub 6 minus 1, which would be 5. So the fifth term, which in this case is 80, times R, which we know to be 2, and that comes out to 160. So this is really all it is that you need to know. So be on the lookout for the homework video. Catch you guys later.